Okay, so I'm going to share my screen now. Can everyone share my screen? See my screen? Okay, I'll take that as a yes. Anyway, so the third problem this week was called 2D Tempo Run. And basically, it's like a 2D matrix, but and you start at any cell in the top row. And then every time you move either one down or one down, one left, or one down, one right. So your end goal is to reach the bottom row and obtain the highest sum of values on your path as possible. And the bounds for this problem is the matrix is at most 1,000 by 1,000. So clearly a n by n O of n by m solution works because that's just about 1 million computations and that's pretty fast. And the strategy we are going to use is called dynamic programming, which gives this O of n by m solution. Except I'll be like presenting two versions of the solution because there's like two ways to do it. Okay, but first I'm going to explain the logic behind dynamic programming for this problem first. So I guess I'll copy this matrix over, and then I'll just explain the dynamic programming based on this input. Right, okay, that should be good. So basically, let's consider an arbitrary square. Let's say we consider this 2. Basically, let's suppose that we want to find the maximum value of a path from the top to this arbitrary square. And basically, you know that the maximum value at this arbitrary square is equal to the maximum value from to get to one of these 3 squares and add on 2, because the 3 possible directions that you could possibly use to end up on the square with the 2 is either from the 4 moving down 1, right 1, from the 5 moving down 1, or from the -1 moving down 1 and left 1. Therefore, we can say that, let's say dp of a, b, the formula for dp of ab is simply equal to dp a, b, okay, let's let a represent the 8th row. So dp a minus 1 b, dp a minus 1, b minus 1. Let's let b represent the bth column. And then dp a minus 1, b plus 1. So dpab is equal to the max of these and add on the value at ab, value of ab. So if we know how to compute that, then basically at the end, our answer is the maximum values of dpab for all the different values at the bottom. And the maximum of all the different dp values at the bottom will be our answer. And now we have to think about how should we compute these dp values in an orderly manner. And basically, there's 2 ways you can try to do this. And I will just go to code the first way now. Okay. So we start off by first reading in the input. I don't think it's necessary to use buffer reader in this case, but I'll just use it anyway because it's faster. We'll instantiate a string tokenizer to read in. The first line contains N and M, so we need to read in that. Oh, oops. And after reading in the input for N and M, we need to read in the matrix, which we will store by N by M matrix naturally. Okay, and after that, we should have read in all the input. Yeah, and then I'll present the first way to do the DP. So the first way we're going to do the DP is basically we're going to start from the top and compute DP values going from left to right and then going from top to bottom. So we'll compute it for the values at 4, 5, -1, 0, then 3, 2, 7, 8, then -1, -2, 1, 1, then 9, -5, 6, 5. The reason that this works is that, like, suppose we are at a value, let's suppose a different value, number 1, right here. We ensured that it is given that we would have computed all these values beforehand. And the values that we're looking at for 1 is based on these values. Since the values we are looking at are already computed, we know for sure that like we can compute each value in the DP array, DP matrix in O of 1 time each. So overall, since there are n times n values, that will be a O of n times n time complexity solution. Okay, now I'm going to go and code it out. So basically what this line of code does is initialize the DP array. Since when we're calculating the dynamic programming values, we want to find the maximum of these 3 values plus this. So since we want to maximize the value that we achieve, therefore, when we are setting it to -1,000,000, we're essentially setting it in this case to -infinity, so that like when you take the max of this initial value with any other number, it'll result with the other number. And that's why we're initializing the DP array with -1,000,000. Okay, and this line of code initializes the values in the top row of the DP matrix as the value of the corresponding element in the array matrix. So for instance, DP of 00 would be 4, DP of 01 would be 5, DP of 02 would be -1, DP of 03 would be 0. And these DP values are all automatically correct because obviously, like, since you're starting from the top row, the maximum value you can get by visiting, by getting to one of these values is just the value itself. So that's why we can initialize it as those values. And typically in every DP problem, you need some initial values to kick off the solution. And in this case, these values serve as the initial values. And now we are going to compute the actual DP values for the rest of the matrix. Okay, so this is how we're going to compute the rest of the values. Like I said, we're going to loop from go from left to right and then advancing down a row after each like loop. So basically, we go down the rows. This is going down the columns, and here we are at an arbitrary point A, B, and we need to calculate it based on the previous values we've computed. And so this if condition checks if B is greater than 0, because in this case, we are considering the case where we are coming from A -1, B -1. And obviously, in order to do that, your B value has to be greater than 0, because if it were 0, it'll be coming from off the grid. Like suppose like we are right here, the B value is 0. And in order to come from the left, you need to come from off the grid, which is obviously invalid. And so then we do this is the max of the original value and the DPA -1, B -1 plus the value at the position. And then on the other hand, we look at if B is less than N -1, when we consider that we are coming from the right, from A -1, B +1. Suppose we are right here. This has a B value of N -1, but if we're coming from the right, we have to be coming from off the matrix, off the maze, and that's obviously invalid. So we need to check if it's less than N -1, and then we compute the DP value based on that in a similar way to the last time. And then finally, since our A value only ranges from 1 to N -1, we know that it's always valid to come from the upwards direction. suppose we're right here, we can always come from 7. Suppose we're at -2, we can always come from 2. So we'll know that it's always valid, and we don't have to like check it with an if statement if it's valid. And we just compute the DP value based on that. And these consider all 3 possible cases. Therefore, the DP value is accurate. And we have looped through all the different values and computed the DP values for every single point. And now we just have to print out the answer. The answer will be stored in a variable called max. And basically, we'll just loop through the last row of the DP matrix and look for the optimal solution out of all those. And then we print the answer. So this should be right. Okay, compile error. I am not sure. Wait, maybe this. Oh. Oh, let me try again. Okay, yeah, it was because I didn't draw IO exception, which you have to do when you're reading an input from buffer reader. And so that passes all the test cases. Okay, so now I'm going to present the second solution, which basically, instead of like calculating the DP values based off of matrix, we'll be using recursion. And I guess I'll just use this once more. Basically, at the end, we got our answer from looking at the last row of the DP matrix, because you have to end up at one of the elements at the last row. So therefore, we can calculate our answer from the last row. Instead of going in order from left to right, top to bottom, this time we'll go sort of from bottom to top with recursion. So we'll start off by looking at 9, and then we'll directly try computing the value of 9 without going to the previous pre-computed values. And basically, if we're at 9, we want to look at these 2 values, but these 2 values will have to look at these 3 values, and these 3 values have to look at these 4 values. And you might think that it's pretty inefficient, because then you move on to -5, and then -5 has to look at this, then this, then this, then this. But what you quickly realize is that when you calculate a value once, you can just store it in a matrix for further use later, so that no matter how you do it, you ensure that you will never calculate a value at a certain position more than once. Therefore, the time complexity has to be O of n times n, O of n times m, because there are n times m values, and you can only compute each value once. And yeah, that makes it O times n time complexity solution still. Yeah, I'll just code it out. I don't know if that explanation was really that clear. I think it'll be easier if I just code it. Okay, so when it's recursion, you have to use a method. So I'll set up my input so that it's outside, and I can use it within the method. Okay, let's just assume that these things are read in. I'll deal with all the rest of the code later. I'll just write the DP function first. Okay, so basically, let's suppose we are at an arbitrary xy, and we are trying to compute its value based on, basically, yeah, we are trying to compute its value. So we know that if x is equal to 0, meaning it's in the first row, then we can just return the value as array of 0, y. Because like we did here, we know that the initial value, if x is equal to 0, is just the corresponding value at its position. So this is basically transferred over here. I like to mention that like the recursive solution is like a lot of it will be pretty similar to the original DB solution that we coded. And then if it's not, then we check if there is a previously computed value at the spot we're looking at. And if there is, we return it because we don't want to compute the value again. So for example, at 9, we have to look at all these values. But when we move on to -5, we're going to have to look at like a lot of the same values again. For instance, let's suppose we are considering -2. If we go from 9, we will have to consider it, and it will compute the value for -2, and it will store it within the DP matrix. But when we move on to -5, we're still going to have to consider the -2. But this time, since we already computed it, we can just return the value already stored from last time so that we don't have to compute it again. And this is basically what this if statement is doing. And now, okay, if you made it back past this point, that means you're in one of these values, you're trying to compute one of these values, and your value has not already been pre-computed. Therefore, at this point, you just have to like recurse based on previous values and just compute it manually now. So then the next part we code will be very similar to this part, except we'll be doing it recursively. Okay, so basically you can see from this part that it's basically the same as this code from our previous code, except it's in a recursive form. And basically what this does is compute the values based on the recursive values we get from doing recursion based on the 3 possible scenarios. Yeah, I think this code is self-explanatory. And then we just return the DP value at the end. Yeah, okay, and that will be our recursive recursion. And I guess I'll just fix up this code.
We also in the recursive method you put equals instead of a plus.
Where is that? Which line? Oh, I caught
18.
it. I think most of this code should stay the same, so I won't write it again. DP. Yeah, we still initialize it with the same values, same logic as last time. I think after this point, it's fairly different. Yeah. Okay, yeah. And then we still have the max, which stores the answer, and then we loop through the bottom values. And this time, instead of just looking at the previously stored values, we have to call the recursive value to actually compute it. So instead of this, I will call recursion n-1a to actually compute the value. And then, yeah, I think this solution works. Let's see. Okay, yeah, it does. Okay, I'm not entirely sure if that last explanation of the recursive values was entirely clear. So if you have any questions, please ask now. Okay, I'll take that as a no. Okay. So I guess I'll hand it over to Victor. He's going to explain it further.
Okay, so basically, I actually made that problem 2D Temple Run as like a simpler version of this other problem. So I guess I'll like walk you guys through that problem right now. And I'm not gonna actually code the solution to this problem. I'm just gonna like talk about it. So basically, in this hard. Hello. Okay, so basically in this version of the problem, so like there's still this n by m matrix that you're given, but in the simpler version that y'all are given, there is this person called person A who starts somewhere at the top, and then he can choose to at every like moment to move in one of these three directions until he reaches the bottom row, and then he stops. But in the harder version, there would also be a person B who starts anywhere on the left column of his choosing, and then he makes three very similar options, and moves from the left column to the right column and stops when he reaches the right column. And then you also have to satisfy the constraint that that person A and person B meet up at least one location. So at least one time, person A and person B are occupying the same cell. And then the problem asks you to maximize the sum of the values that person A walks on plus the sum of the values that person B walks on. Okay, so first of all, what ideas do you guys have about which cells are possible for person A and person B to meet up at? Like, for example, is it possible for person A and person B to meet up at this top right corner?
No.
Okay, so yeah, it's like, for example, it's impossible for A and B to meet up here because B would have to travel all these columns across in order to get here. But then A starts at the top row, and then by the time B gets here, A will already be like long at the bottom row. So what kind of like observation does that tell us about where A and B can meet? All right, so basically, person A and person B have to have traveled the same number of steps from their respective starting locations in order for them to meet somewhere, right? So person A has to have traveled the same number of rows as the number of columns that B has traveled, because at a certain point in time, they both made the same number of steps. And then A is traveling down one row every step, and B is traveling one column to the right every step. So basically, in order for them to be able to meet up at a point, the row number has to be equal to the column number. So basically that starts at like this point, and then here, and then so on, basically along this diagonal starting from the 0, 0 top left corner. So then basically, okay, so from here, do you guys have any solutions or like have any ideas for a solution to solve this problem? So basically, just like in the solution that Daniel described, we can compute a DP matrix that would tell us what is the maximum sum of values we can get by starting somewhere in the top and reaching this point, right? So what we can do is we can compute a similar matrix, but for all 4 directions. So let me actually create a text box. That's quite big. I don't know how to make this smaller. But basically, I think this might become smaller if I type more. So in his thing, he assigned DP of like IJ to be like the max sum by starting at the top row and ending at IJ, right? So what we can basically do is we can call this DP matrix actually like top. So we're gonna say that that is the best sum you can get starting at the top. And then we basically make a similar thing for like a bot. All right, so basically for so top of IJ plus bot of IJ would be the maximum sum that person A can get by starting somewhere at the top and then reaching cell IJ and then proceeding from cell IJ to follow some path to reach the bottom, right? Because it's symmetrical to start at this cell and reach the bottom row versus starting somewhere at the bottom row and then reaching the cell. So we can compute top and bot in a very similar way that Daniel computed the DP matrix. And then we also need to consider that A and B have to intersect, which means that B would also have to pass through a certain meeting point that we're considering. So we can again make okay, wait. Okay, so we can again make two more matrices that are counting the same thing but for left and right. This is the max sum by starting at left column and ending at IJ, and then right to IJ is the max sum by starting at right column and ending so basically so left IJ plus right IJ for a certain IJ is the maximum sum that someone can get. I mean, that person B can get by starting somewhere on the left column and then reaching this cell and then proceeding from that cell to end somewhere on the right column, which is again symmetrical to starting on the right column and then reaching cell IJ. So basically we can loop through, after we compute these 4 DP matrices, we can loop through all the possible meeting locations, which are when R equals C, and then add up the sum of these 4 values, like left IJ plus right IJ plus top IJ plus bot IJ, and that will be the sum of the values that person A walked on plus the sum of the values that B walked on. And then we would take the maximum of that over all meeting points, and then that would be our answer. So does anyone have any questions over this solution? Okay, I think no one has questions. So actually now we're gonna post the link to next week's contest. So I will pull up that link right now. Okay, so I think this contest is open now because we set it to start at 3:30. Oh, actually starting at 3:30. Wait. I think it's starting at 3:30. So basically in like 4 minutes it'll open. But other than that, that's the end of this meeting. So thank you guys for coming. And yeah.